right, great. Next up, we have Laura Khanna talking about integrated hardware decoders. Laura, take it away.
Thank you. Hi, my name is Laura. I'm a quantum scientist at Riverlane, and I will be talking about our progress towards integrating our hardware decoder with Rigetti's control stack. So this has been a collaboration between Riverlane and Rigetti. So Rigetti have recently made available their Ankaa 2 QPU, which is a quantum computer with 84 tunable qubits on a rectangular lattice. And this rectangular lattice suits surface code experiments. And Rigetti have also enabled mid-second measurements, which means we can now do multi-round QC experiments. They're also focusing on improving fidelity, which suits nicely the goals of achieving fault tolerance, since we want to be below some threshold. And Rigetti also offer pulse-level access, which means we can do tailored QC codes. So now we have this device we can run surface code experiments on. Of course, we need to be able to decode. And this brings me to kind of the main motivation between the two companies working together, which is that we want to get to real-time decoding. So in order to get to full fault tolerance, we're going to need some non-Clifford logical gates, an example of which is a logical T gate. And a way to obtain the logical a way to do the logical T gate is via state injection, which I've shown in the circuit here. And as you can see, there's a logical S gate that depends on the measurement outcome of one of the logical qubits. So that's kind of highlighted in green. And Barbara Terhall, in her paper, showed that if we're going to have to do this decoding mid-circuit, the decoder is going to need to be able to process the data at the rate that the data is received. If here in the mid-circuit, when we need to decode, if we're actually slower than the rate at which we receive the data, we're going to encounter a backlog problem, which causes exponentially slower computation, which is, of course, not what we want. And on superconducting devices, this generating data can be as fast as 1 microsecond per QEC round. So this means we really need fast, real-time decoding. So at Riverlane, our solution to having real-time fast decoding is to have a dedicated hardware decoder integrated in the control stack. And we've made such a decoder. It supports surface code and repetition code. It can decode up to 1,000 qubits. And it's been optimized to be easily integrated with an FPGA. Earl Campbell gave a talk talking about his hardware decoder in a session earlier today. So if you missed it, there's also a link to the paper on arXiv. So now we have a device we can run surface code experiments on. We have our hardware decoder. Now to get to real-time decoding, we've been working on integrating the hardware decoder in Rigetti's device. So in Rigetti's control system, each qubit is controlled by 6 sequences. And for them, the classified readout results are automatically broadcast to all of the sequences. Of course, the decoder expects to receive these measurement results. But because all the gate sequences receive all of the measurement results, we actually have quite a lot of flexibility with which sequencer we can integrate the decoder with. Moreover, our decoder doesn't take up a lot of space, so we could really be quite picky exactly where it's integrated. In the end, we landed on integrating it with the gate sequencer, simply because it still had the most memory left. But yeah, we could be quite flexible where exactly it sits. Now when we have the decoder sitting in the control, we also need to be able to interact with it. And we do this via the sequencer processor's input-output ports. So of course, we need to be able to send the readout results to the decoder. We also need to be able to set up the decoder configuration. But there's also a bunch of data we want to extract from the decoder so that we can really test the integration and how it's doing. So for example, we read back out the decoder correction bits because we want to know how well it's doing in terms of accuracy. We query the decoder status to see if there's been any failures in the system. We also read back out the measurement and the syndrome that the decoder receives. And then we compare that with the measurements we get at the end of the program to really make sure that the results the decoder got are the correct ones and the measurement propagation was done properly. And we also receive back the clock cycles for different stages of decoding so we can see how fast we're doing the decoding. So this is all quite low level. We want to be able to interact with the decoder at a higher level. So in order to do this, we use some existing and also wrote our own custom assembly language instructions to do things like initialize the decoder, reset it, send the readout results to the decoder, and receive the output from the decoder. In the Rigetti's PyQual language, which is their way to interact with the quantum computer, they have this class called a program, which sets up the exact circuit you're going to execute. And what we did was we inherited from the program class, wrote our own hardware decoder program, which sort of automatically wraps all of these instructions to talk to the decoder to your circuit. So what happens is as you run your circuit, it will automatically trigger the decoder, read from the decoder, send information to the decoder. So you really can write any experiment you want, and all of this gets wrapped around automatically, and you don't need to kind of worry about this anymore. So we've never done this before, so of course there's been quite a few challenges. So here I've listed just a few. So I just talked about how we need to add these extra instructions to be able to interact with the decoder, but there is a limited executable memory in the system. So we had to be a bit careful to not run out of memory and come up with a few tricks to make the program a bit shorter. We also wanted to be able to, so that to get these system, you can decode rather than having a new executable for each shot. You can also have a single executable and run many shots on it. So we wanted to do something similar using the decoder, but in order to do this, we had to be really careful with how the sequencers are synchronized. So that was quite a bit of a challenge. And finally, we also want to be able to minimize the time it takes to send measurements to the decoder. So what we do in practice is we execute our gates, perform measurements, and then we already keep executing the next set of gates and let the readout propagate during that time rather than just sitting there and waiting while the readout work propagates. So now we've actually managed to do this. We have a hardware decoder sitting in the Rigetti's control stack. We're able to run these experiments that automatically do the decoding in real time. And we found that currently the latency between the final measurement and the decoder being able to start decoding is about 1.5 microseconds, but this is still ongoing work, and we think there's room to improve. We've also been using cyclic repetition code with 4 data qubits and 4 ancillary qubits as a sort of test experiment to really kind of make sure it's all integrated correctly and speed test. And what we found is, so currently the decoder runs at 156 megahertz frequency, and with this we see that when we do an experiment with 11 measurement rounds, we get to about 240 nanosecond decoding time per round. But we think there's room for more improvements. So like I said, currently the decoder runs at 156 megahertz frequency, but the decoder being integrated with Rigetti can actually run at 250 megahertz frequency. At the moment, we've just been trying to get the functionality working, but we think there's room to, Rigetti can improve the frequency. But what's even more, the recent versions of the decoder can actually decode at 400 megahertz frequency. So if we do that, actually our decoding time is going to be about 93 nanoseconds per round. And in the paper that Earl talked about earlier today, they also show that actually as the device gets less noisy, the decoding time should also get faster. So as we keep working on the QPU, the decoding time should also improve. So to summarize, we have been working with Rigetti using the Ankaa-2 device to run QC experiments. Riverline has a fast hardware decoder. We have successfully integrated this decoder in Rigetti's control stack, and now we can go ahead and run fast real-time decoded experiments. So thank you.
We have enough time for questions. All right. Chair's privilege. I noticed that the you can decode, distance 3, 5, 7, and it takes less than a microsecond, but when you get up into the 20s, it starts to get a bit awkward. Some people think distance 31 is going to be necessary in order to get to the promised land of running, the big adult algorithms with surface codes. What new advance are you going to pursue? Just higher frequency FPGAs or something algorithmic?
Sorry, I'm not actually sure what you meant. So we actually
right
had 11 measurement rounds. We
it's
did
forward
get
one
to.
slide.
Do you need this one?
Yeah. So on the right side, there's a decoding time per round versus code
Yeah,
distance. And if you wanted to get up into the things, I mean, well, okay, first off, distance 7, 9, and 11, handy,
Yeah.
right? Nobody's doing that yet.
Yeah.
But what are you going to change in order to get to like big double-digit distances, like 30-ish?
Yeah, so like I said, we can go up to 400 megahertz decoding frequency. So we think that will be plenty to get to fast decoding.
Okay, so all the numbers on the right are from 150.
I'm actually not fully sure, to be honest with
Okay.
you. Yeah, I need to go double check. Sorry. Yeah,
That's okay.
I would believe it's, yeah.
And there's one more question while we're switching stuff
fine.
around.
Hi, Laura. Thanks for a very nice talk. So I remember you mentioned the parallel window decoding, right? So is this decoder compatible with the parallel window or not?
So the one we have integrated with the Getty is a fixed window decoder, but we do also have a sliding window decoder that we're working on.
So as I remember, the sliding window decoder requires to commit only part of the decoding results. So current decoder just output one single bit. Am I understanding correctly?
Yes. So the current one, yeah, just sends you the final correction bit.
Got it. Got it. Thank you.
So there will be some changes we need when we have the sliding window.
Yeah, that makes sense.